Begin recording. Okay, I think, well, I have the good part, and I think arguably nonlinear analysis is the funnest part about this performance design of tall buildings, right? But I have a lot of slides to get through, so let me get right to it. I think Ron Hamburger gave a great introduction this morning, and just that it's really been about 20 years that nonlinear analysis has really been getting into practice, and in fact, we're still figuring out things, so that makes it kind of exciting, but on the flip side, you still have to kind of think about things. It's not all cookbook yet. I listed all these documents here. I'm not going to talk all about them, but as Ron talked about this morning, though, kind of one of the landmarks for getting nonlinear analysis thinking into practice was the FEMA 273 in 1997, which in its modern version is ASC 41. So that's one of the documents that I'll be kind of referring to as I go through today. Also, the tall building documents we've been hearing about, and in particular this document ATC 72, Modeling and Acceptance Criteria. There's also been a NIST tech brief that I was involved with that put together some other guidance on nonlinear analysis, and things are kind of continuing. But as Ron mentioned, it was really the FEMA 273 kind of introducing static pushover analysis apart from the performance framework that really got some of the key essence of thinking about how you do nonlinear analysis for design into practice. That distinction between the elements that are the so-called deformation controlled and force controlled, and the key thing there is the ones that are deformation controlled, those are the ones we have to model non-linearly. Those that we choose to model elastic, by definition, will be force controlled, and their acceptance criteria determined accordingly. But to me, like the big improvement that came with FEMA 273 and ASC 41 now is that it provides tables like these with modeling criteria for different kinds of structural components, in this case relating the deformation capacities and so forth, the reinforced concrete to tie spacing. And this is, I think, what, as a practitioner, really lets you do nonlinear analysis and doesn't make it a research project each time to come up with your nonlinear analysis model. So I think we're building on ASC 41. I think we should keep in mind that ASC 41 really was developed thinking about rehabilitation of existing buildings. Also, in pushover analysis, it's really kind of focused towards that. And while there's been improvements in pushover analysis through the years, some of the modeling criteria have not advanced dramatically, in my view, in ASC 41. And I think that's where the things is we're starting to use nonlinear dynamic analysis in the tall buildings where we're trying to push it, and documents like that ATC 72 as additional information there. So it's really these tall building documents that might be really embraced, going from static pushover to nonlinear dynamic analysis. And I think correspondingly, if you look in practice, a lot of this builds on the tall building documents, relates to kind of ASC 7, the loading criteria. And as Marshall described, ASC 7 is really where we go to define ground motions and the hazards and so forth. ASC 7 really didn't give much guidance on how to do a dynamic or a nonlinear dynamic analysis, but that will be changing with the next edition of that. And you could get a glimpse of what's coming forward is this NEHRP 2015. Marshall talked some about it, but what it does is it has a new draft chapter 16 for ASC 7 that gives more guidance on nonlinear analysis. And in fact, that really embraces and was modeled after a lot of the ideas that were developed through the tall building initiatives. Again, this is the document ATC 72, which I worked on with Helma Krawwinkler, John Wallace, Jim Malley, and others. That's trying to go deeper into modeling and some acceptance criteria, thinking about the cyclic behavior of components and envisioning these used in nonlinear dynamic versus static analysis. And finally, that tech brief that I mentioned was put out a couple of years ago with NIST, kind of giving some high-level guidance on using nonlinear analysis in design. Another thing being worked on currently from NIST is a roadmap for future research and development in nonlinear analysis. And in fact, one of the products that will be coming out of that over the next few years will be more detailed design guidance for nonlinear analysis on moment frames, shear walls, and so forth, starting to fill in kind of more of the gaps and develop things further. So things are getting better in terms of distilling down information, but we're still, when folks are doing this in practice now, you still have to reach out and be aware of the latest research coming, looking at papers, depending on what type of structural system you're looking at. So there's been talk about capacity design, and just as a design principle, there's many advantages. The idea of making a clear distinction between force and deformation controlled components. And of a lot of advantages for design, it builds reliability into your structural system. Also allows you to focus the elements that are going to be yielding, to put special detailing there. And conversely, elements that are not going to be yielding, you don't have to worry much about the special detailing. So capacity design, the principle is to get a good distinction between those. And I think with new buildings, you have the opportunity to do that much better than, say, in contrast to existing buildings when you're rehabilitating. But I think from the standpoint of analysis, another thing, big advantage of capacity design is that it really makes our analysis easier, okay? Because if we really have well-controlled ductile elements and we know where they are, we have a better chance of modeling them. And again, the messy elements that are force-controlled, that we're kind of shielding from nonlinear actions, we handle those elastically. This is in contrast to, say, modeling an existing building where you just kind of have to model it, the building that you're dealt. So in design, thinking about from design how that can really help your analysis, and the nonlinear analysis give you more confidence in what you're analyzing. So of course, then there's acceptance criteria for the so-called deformation-controlled and force-controlled components. We heard some of that this morning. But from the analysis side, you want to be thinking about, number one, which are the elements you're going to model inelastically. And again, those are the deformation-controlled ones, the other ones being elastic. But also start to think about what are going to be the demand parameters that you're going to need to extract from your analysis model in order to compare to certain acceptance criteria. So is it deformations or strains or so forth? And so if we think about acceptance criteria, first there's some at a global scale, and for example, the Pier Tall Building Guidelines, as you heard, they'll give very prescriptive requirements on what the median or mean drift can be, 3%, the maximum out of any ground motion, 4.5% story drift. If you're looking at more broadly performance-based and looking at damage, there might be peak floor accelerations. So these are kind of at a global level. But then when you start to look at specific components, you have to ask yourself, how am I going to be modeling those? And conversely, what's the acceptance criteria that I'll apply to those? So for example, if you're looking at beams, you could be looking at a hinge rotation. And of course, when you look at ASC 41 and others, they'll give acceptance criteria and modeling criteria based on rotation capacities. But when you look at other things, you might be starting to be looking at strain deformation quantities. So you got to think carefully in building your analysis model to think ahead to what measurements you want to get out of that. And you can also think about those measurements. Are you just looking at peak measurements? Oftentimes we'll look at, say, peak rotation or peak strain values, sometimes residual, but there could be cases cumulative. For example, buckling restrained braces have a criteria about the number of strain cycles they could go through. So that's something you might want to be pulling out of your nonlinear analysis. Also thinking about whether you're thinking of if it's a deformation quantity in a hinge rotation, is that total rotation or plastic rotation? And again, there's no hard and fast rule about which is better, but just thinking up front about what it is you're modeling and how you're going to compare that to certain acceptance criteria. Force-controlled components, on the one hand, seem more straightforward. You calculate a force in a member, a moment or shear or so forth, but sometimes you start to get down to, for a continuum in walls, kind of a stress level component. And there you have to start to be thinking about over what area that you're integrating that stress. Is it kind of an average stress over an area? Because we're all familiar with thinking about stress concentration. So when you start to get into things modeling at the continuum, you have to be thinking of that as kind of a gauge or an averaging area. So shifting gears a little bit, we heard Farzad mentioned this morning, when we're building the nonlinear analysis, the most important thing is that we should be thinking about putting in median model parameters. Median being kind of a central tendency value, and median and mean for most of the parameters we're looking at, we don't have enough data to actually differentiate the two, so you could think of them synonymously. But that is putting in the expected strength and stiffness of your concrete and steel elements. When you look at deformation capacities, when you're putting in hinge rotation backbone curves, these things should all be kind of like the average value, if you will. So we want to be starting our analysis from capturing kind of the average behavior and then think of things from there. This is kind of contrary to what you might do in certain practice, where our tendency as structural engineers is to, quote, be conservative, given a lower bound on the stiffness. But the idea when you're combining shear walls and frames and other elements and everything, what's conservative is really unclear. So the key message here is start to, every modeling parameter that you put in, think of that being kind of an average value to start with. So then taking those models, and we'll see examples this afternoon, this is some slides from MKA, building the analysis model, putting through the ground motions, and again saying, what are you going to get out of your analysis model, and how are you going to evaluate that? This is looking at, say, story drift ratios, or it could be looking at force components and elements. This is an example looking at, say, the total shear force in a core wall. But when you go down to checking the strength of the core wall, you really do that more based on panel, so looking at those things. So just examples of the output that's going to come out of your analysis. So think of that as you're building your model, choosing your software. Now I did want to bring up, you see in those slides that I just showed, there's variability in our output. One of the things in doing these nonlinear dynamic analysis, it's kind of unsettling because it looks like there's more uncertainty in our designs than there ever was. But the fact is that uncertainty has always been there. And you can think about, we're checking things at MCE level ground motions, let's say. There's uncertainties in even how we define that MCE. When you look at the hazard functions, they're mean annual frequencies. So there's uncertainty about that mean of just what the MCE level intensity of ground shaking is. Then there's these so-called ground motion characteristics, and you see that when you take 7 or 11 records due to we index them based on spectral acceleration, but based on different frequency, content, duration, and so forth, you get randomness there, something we'll call record-to-record uncertainty. And that really comes out explicitly when you look at plots like these from, say, taking 7 ground motions that are just scaled up. You see that record-to-record uncertainty. But also recognize there is structural modeling uncertainty, that is in the parameters we build into our analysis. So while we're starting with a median model, and in general a lot of our criteria are then going to be acceptance criteria about the mean demands on drifts or the mean plus a standard deviation or some factor of that, to recognize that's all from a mean model, that unless you start to vary the modeling parameters, you're not even capturing, if you will, that so-called modeling uncertainty. So keeping this in the back of your mind, the tall building criteria, what's nice about them, they're fairly prescriptive. Again, it's not a research project you have to get into, but to keep in mind that there's a lot of uncertainty hidden behind that. So for example, when we calculate the drift demand, and there might be a cumulative dispersion of 0.5 to 0.8, essentially a coefficient of variation on our calculated drifts, for these parameters I described in the ground motion, the record-to-record, and modeling uncertainty. So what you can think about when we're checking our mean drift demand against this 3% limit, 3% story drift, that if you put in the values of dispersion I'm talking about, you could think, well, it's really giving you, by checking the mean at 3%, it's really saying that there's really less than 10% chance that your drift is going to exceed 5 or 6% drift. So we're checking it at 3, but our real check is, considering the uncertainty, a higher drift level. Or you could take that, and by the way, when calculating that mean, based on the number of records that we're using for that, this is an example, if your underlying drift, say, has a dispersion of 0.5, that if you're checking and calculating a mean value just with 7 records, there's even just a variation in that value of the mean. That's an estimate of the mean. Okay, so keeping all these things in mind, because sometimes we'll take that mean as, well, it's 3% or 3.1%, it's red light, green light, but recognize that that's just an estimate to begin with. And even trying to get standard deviations out of 7 records, you don't even want to try to do that. In fact, the tall building criteria gives you some allowance to consider the standard deviation, but it's putting limits on it, recognizing that that measure of standard deviation from 7 or 11 ground motions is very limited, of limited reliability. Now thinking of the drifts, taking that example a little bit further, if we believe there's a drift capacity that we could define, and there's some dispersion in what that capacity is, then you could again look at this 3% limit on our mean drift, and when you factor in the dispersion both on the capacity and the demand, that's essentially saying, well, if you have a mean capacity of 7 or 8% drift limit, that by checking the 3%, you have a less than 10% chance of exceeding that. Okay, so again, the values that we're seeing, 3%, are pretty modest levels of drift in terms of nonlinear behavior, but recognizing we're really essentially protecting against much larger drifts than that, owing to the uncertainties that are not fully captured in our analyses. And the same is true of strength-controlled components. And that's why you see these factors in front of the mean demand of 1.5 times the mean demand has to be less than or equal to the capacity of a strength-controlled component. And even that 1.5, which seems high, that's still giving you a less than 15 or 20% probability of failure. You'd have to go up to a factor of 2 times the mean to get down to 10%. And that's, so part of what's factored into that, and as far as I've mentioned this morning, we'll characterize strength controlled as either critical or non-critical components. And partly that's trying to factor in, well, what's the consequence of the failure of a force-controlled component? If the force demand exceeds the strength of a force-controlled component, how catastrophic? What would be the effect on the building? And based on that, by making those categorizations behind the scenes, we're really kind of saying, well, we'll allow a higher probability of failure for those elements that are non-critical. So sometimes, but I emphasize these points because when you get into doing these analyses and calculating all the numbers and statistics, we take them kind of very hard and fast, but to recognize there's more uncertainty in the problem, and sometimes our methods will pick up. And I think one area, as far as I'd mentioned, he promised this morning that Greg would talk about this, Greg would talk about that. I was sitting there going, I'm not going to talk about any of that. But one of the things he said I'd talk about would be the backstay effect. So I created this slide this morning. You don't have it in your handouts. But, you know, the backstay, in other words, is you have the core wall coming down through the below grade. You know, how much shear you develop in the shear wall below grade, or how much force goes into the collectors, depends a lot upon the stiffness that you put into the shear wall versus how much you have in the foundation, how much you have in the floor diaphragm, how much the soil that's leaning on your basement walls is contributing. If you look at this example, and these are, by the way, examples out of that ATC 72 document, you could look for more details on that. But, you know, the example on the right where you have a structure where the podium structure, you know, goes up 5 or 6 stories, and you have kind of 2 shear walls there, one in the low-rise building, one in the high-rise. To think, okay, if I'm analyzing this with a median model that's not picking up any modeling uncertainty, what can you do in those cases? So the real guidance is to do some selected sensitivity analyses. Take, you know, in this case here, if it's sharing of load between 2 walls, you know, make what you think are some reasonable variations in what the stiffness properties of those, just to have confidence that something dramatic's not going to happen in terms of your estimates, say, of forces on force-controlled members or deformations and other components. Because ultimately, the code doesn't relieve you of that responsibility, even though it gives prescriptive rules. And as far as I've mentioned, practitioners might hate this because you got to go run more time history analyses, wait a few more hours. So it's a matter of using your judgment in terms of when things are really important, you know, when there might be a dramatic difference in the calculated values due to the assumptions made in your model. Okay, I'd like to shift gears and talk a little bit about the modeling attributes. You saw this, something of a slide similar this morning, but to think about, like, if we think about beam column, modeling beam columns, we could have kind of the so-called simplified or phenomenologic one shown on the left, where we kind of categorize the inelasticity in a nonlinear rotational spring. You could go to the right side where we have full-blown continuum finite elements, and then something in between, a distributed plasticity fiber element. So in coming into a problem, it's a balance of saying what level of accuracy do you need, or can you get out of your analysis, what's practical to do. And the choice of these things will vary depending on the specific circumstances and kind of what's important for your design. So the simplest, I shouldn't say the simplest, they look like the simplest in our analysis model, these phenomenologic models, you know, a plastic hinge. And these are fairly well developed in the literature, especially uniaxial ones, or single degree of freedom. You can model all these sorts of degradation that's shown on the right. What's not simple about them is then how do you calibrate those back to data, to test data, to capture these effects. And recognize when you're modeling, when you take a phenomenologic model and compare it back to test data, the only thing that can represent are the things that happen in the test data that you're representing. That is, to extrapolate these models gets kind of dangerous to larger sizes or so if you've not tested things at those scales. But they have the advantage that some of the hysteretic rules are pretty fairly well developed, and they can also capture phenomena for which our underlying fundamental understanding is not fully developed. Going forward, though, you could go to places thinking about doing fiber-type models where we're capturing the distributed plasticity through a cross-section and along its length, or over to continuum-based finite element models. And this is an example shown in the slide here. You know, if you're really trying to understand something about, say, a haunched reinforced steel connection and the effect of local buckling and fracture, our continuum models are getting to the point that they could start to kind of pick up those effects. I mean, there's still limitations there, but of course it's substantially more effort. But the idea is if you don't have a phenomenologic model that captures some of these details, sometimes you could selectively go into deeper continuum models that you wouldn't analyze the whole structure with them, but you might analyze components with them to help inform your analysis. And the same, and again, the story is different depending on whether you're dealing with a frame or whether you're dealing with a wall. Interestingly, ASC 41 for walls gives acceptance criteria in terms of hinge rotations. But in fact, when you look at these core wall structures with coupling beams and odd shapes and so forth, you really can't go look at the rotation at the base of a wall. So really there you're forced into using these kind of continuum or something in between, these kind of fiber type models representing the shear walls. A few other things on kind of the component models and how we're representing things. This slide is showing that, the slide on the upper left, some hysteresis loops of tests that were done on identical structural components. One test that was done monotonically, and you see something has fairly large ductility there, versus under a cyclic loading protocol. So one of the things that's come up as we start to think about dynamic analysis and the difference between monotonic and cyclic are thinking about monotonic backbone curves. That would be the curve that kind of traces the envelope of response from a monotonic test. A cyclic envelope is one where you do a cyclic test and you trace that same envelope there. And shown in the lower right, generally the monotonic is going to envelop the cyclic envelope, but to understand also that the cyclic envelope really depends on what kind of cyclic loading protocol has been used to test a component. So shown in the upper right of this slide are some examples. Qiaoming Wang tested some, these are wooden shear walls, but demonstrate that for different cyclic loading protocols, you in fact get very different cyclic envelopes. And just to be aware of that when we're kind of developing our models. And kind of why is that important is that when you start to do dynamic analysis, this is an example of, say, analyses that were done under two different earthquake records. One of the Chile records shown on the left side has a lot of cycles in it, so a lot of cyclic degradation is happening there. Whereas the Kobe record is shown on the right, which even though it's cyclic loading, it's really the big damage is done in one pulse. And so the idea is, if you could have a model that could somehow transition from capture the monotonic response, which could occur under a very pulse-like record and take advantage of the strength and ductility your structure has for that, but can also degrade itself down to pick up the cyclic effects that's shown on the left, that would kind of be the ideal model. We're developing some of those in research. They're making their way into programs, but they're not fully there right now. So at this point, it's just to be aware of kind of these factors and to think about how you're capturing that with your analyses. This is an example showing kind of an extreme case, taking two cyclic models, and the time history traces shown on the left show if you do a dynamic analysis where one model, the structure is collapsing, and where the other model, the structure gets some residual drift but doesn't collapse. And it's coming from those two models shown on the right. The one on the upper right captures something we call in-cycle strength degradation. That is, when you go over the peak, the curve drops down with a negative stiffness. The one in the lower right is a cyclic model. Helmut Krawwinkler would call these happy springs because they never experience that strain softening behavior. But in fact, if you did tests of a component and you drew a cyclic backbone, you wouldn't know the difference between these two. Okay, so the point is to recognize when you use these cyclic backbones to then look back to how does your analysis program have a model that represents that descending stress strain curve, or is it a so-called happy spring shown on the bottom here? So this is from the NIST tech brief. I won't go through all these plots, but trying to categorize the different types of degradation. I think the one thing that's important to be aware of is that if you are doing an analysis where you're going to deform something past this peak where it starts to get a negative slope, to really make sure that your analysis can, number one, pick up that negative slope, and then to understand whether your analysis can degrade in that backbone curve due to cyclic loading or not. And that's where we come into these, what were described as 4 options. Here I've kind of folded them down into 3 options that are described in the ATC 72 and then in the Peer Tall Building Guidelines. It's to ask the question to say, in the cyclic models in your analysis program, do you have option one that can, which is the quote best, which can model the full monotonic response, pick up pulse-like motion, but that if there is cyclic behavior that occurs before that, that it will chew away at that backbone curve and degrade things in. So it's capturing the behavior as realistically as we can. Option 2 and 3 kind of put together here. These are ones where you say, well, in my analysis program, the backbone curve has this negative stiffness, but that backbone curve is fixed in the analysis model. So as many cycles as go by, that backbone curve is going to be fixed there. And it's picking up that negative slope, but it can't degrade. So that would be kind of option 2. Option 4 at the bottom, that would be the most limited. This is where you have a model that doesn't have that negative slope, that if you pushed it monotonically, it would keep increasing its resistance. And there you basically just have to cut it off. You could use that model up to the point at which the structure degrades, but your model doesn't. And so the ATC 72 document and some of the criteria in there give some guidance on modeling parameters for these different options. Taking this discussion and thinking back to ASC 41, that in fact the backbone curves that are given in ASC 41 really match that option 2 and 3, because those are cyclic skeleton curves from cyclic tests that folks have done. And so they have that negative stiffness, but it's kind of a fixed backbone curve. And in fact, my sense is that most analysis programs tend to have models nowadays that can capture that effect. They don't degrade the backbone curve. So if you will, it's pre-degraded. But if you're basing it on ASC 41 type models, these cyclic backbones, you're picking up that effect. A couple of other general comments we heard this morning. We want to always be including P delta or second order geometric nonlinear effects, because these will both reduce your effective period of the building, reduce the effective stiffness. They'll also amplify the internal forces. And the key thing is, even when your structure is responding elastically, this might be a modest effect. But when your structure starts to go nonlinear, that whatever P delta negative stiffness was there, it's going to have an increasingly important effect when you do the nonlinear analysis. So even if in linear analysis you say, well, P delta is not a big deal, for the nonlinear analysis, due to the softening of the structure, it is. And of course, with your 3D models, and Farzad talked this morning, how the 3D model should include kind of all of the mass and load that's in the building. So you can't just model the core wall and put a horizontal mass there and not have the vertical load that's associated with that mass. So to make sure that that's represented in your model, and that's why the guidelines then give some guidance on what load to use for the gravity load. And here again, these are expected values. We're not putting the 1.2 dead load. We want to get kind of the expected load and keeping with the idea that our model should represent characteristic values. I'd like to switch gears and talk about modeling specific structural components. First, looking at reinforced concrete frames, where generally I think when you look at what's being done in practice, these would be done with concentrated hinge type models. If you look at the different varieties that are out there, the hinge type models capture things pretty well. There's these resources. You have them in your notes here. I'm not going to read through them all to go for more details of these. And I think if you think of the status of these models for reinforced concrete, in fact, we have a lot of data on beam columns in concrete. And I'll show some examples of that in a couple of slides. More limited data, in fact, on beams. Even though our beams are the things that yield in our structures, we have considerably less data on yielding concrete beams than we do concrete beam columns. Even less on problems with splices and things, but that shouldn't be a problem in modern buildings as compared to existing ones, trying to model an existing building. And there's fairly well developed uniaxial models, moment versus hinge rotation, for example. There's PM interaction, which capture the interaction well, but the degradation and the cyclic degradation not as well. So I think as researchers, there's room to kind of further develop the multi-axial PM interaction to include some of these cyclic degradation effects. This is actually one of the system types I'm most familiar with, having worked with a number of students. There's actually a database available through the Peer Center with over 250 columns, which we've then calibrated models to. And as we've calibrated different modeling coefficients, I like to distinguish between those that are shown on the left, I'll call semi-empirical. What's the stiffness or what's the strength of in this case, a beam column? We have theories to give us moment of inertia. We have theories to give us yield moment. We still calibrate that to test data to make sure it's kind of fitting things properly. But then there's other modeling parameters that are important for nonlinear, such that the rotation capacity beyond which you start to degrade, or this post-degradation slope, which become increasingly important in our nonlinear models. Those are things for which we don't have good theories to predict. So I call those purely empirical. We have sense of what affects rotation capacity, axial load, tie spacing, but we don't have a theory to tie those together. So it's more empirical. And consequently, we tend to have a lot more dispersion, variability in predicting those parameters. These are a couple of slides on effective stiffness. Some of them shown up top from the ATC 72 document, some from the ASE 41, and of course the PEER and the LA TBI guidelines distill these down to 1 or 2 numbers. But just a key message on effective stiffness is, one, there's a lot of variability in it. You see that in the picture shown below. It's affected, of course, by axial load, the effective stiffness of elements. But also, whatever we put in an effective stiffness, is essentially it's a secant stiffness. So it changes whether you think you're doing a serviceability analysis, where you're not going up and yielding components, versus whether you're doing a nonlinear analysis where you're going to be yielding, where your secant stiffness is up to yield. So much different values, so to be aware of if you're doing analyses with different expected drift or deformation levels. This is looking at rotation capacity from this, going through this database, doing regressions. This is an example of what we provide in ATC 72, where rather than a table of values like you see in ASE 41, here we have an equation where we're looking at different parameters that can affect the rotation capacity. That's the good news. We have this nice tidy equation. The bad news is you could see the dispersion in the data in the lower right, coefficient of variation of about 0.5. Okay, so when you put one value in your model and use one acceptance criteria, just remember that coefficient of variation is lurking back there. The post-peak becomes very important. These are some examples of tests Jack Maley and his students did a few years ago. Columns with axial load above and below the balance point, they have about the same moment strength as predicted by theory, but dramatically different post-peak response. And so we're trying to, in the models that are out there, picking that up in this theta PC factor, which will be, going beyond the post-peak and seeing equations there where that new and that's shown in these kind of regressed equations comes from the axial load effect. And these are some examples of the rotation capacities you get out of that. I think for the sake of time, I'm not going to talk too much about those. And if you look in the ATC 72 report, which gives some guidance based on new data and cyclic response, there's some comparisons there to how that relates to the ASE 41. They don't agree exactly. They tend to follow the same trends. But again, this is part of the challenge today, to take this various sources of data and convince your peer review you're using the right stuff. Joint rotations, that always comes up. I think in modern frames where our joints should be stronger than the beams, it's less of an issue, but you still, finite joint size is probably the most important thing there. But also if there is some panel deformation, you could have some of these elaborate type of connection models shown up above. Again, for concrete frames, ASE 41 gives these sort of kind of equivalent rigid zone models shown below based on the relative strength of the beam in the column. For steel moment frames, it's kind of, I could repeat a lot of the same story. In fact, ATC 72, Helmut Krauwinkler and his students developed a lot of equations based on test data. Interestingly, for steel, whereas for concrete we have a lot of columns and not too many beams tested, for steel we have a lot of beams or beam column joints tested and not as many columns. So one thing to be aware of is that if you're dealing with deep columns that tend to have L over R ratios that are higher, we don't understand those as well. In fact, there's currently some tests going on at San Diego by Xiaoming Wang, so I think we'll improve our understanding in the future. And in fact, if you look at the ATC 72 document, it kind of punts a little bit on the deep columns. So just kind of be aware of that they will tend to degrade more due to complicated kind of torsional, flexural, local buckling interactions, things that are tough to capture. And then, of course, also if you have it shouldn't come up in a new building, but if you have existing buildings, being aware of the fracture connection problem. So talking about moving on to concrete shear walls, and these are probably most important because so many of the buildings are built with these. The most popular models to capture these core are kind of like a fiber type model. This is not like one fiber element coming up from the base, but it's actually panels of fiber elements that are kind of put together, where basically you're modeling the stress strain, the uniaxial stress strain of steel and concrete, say the concrete modified for confinement. Typically modeling the shear behavior as being elastic, so that means that's going to be our force controlled component. And again, you see some of the references that are shown there. So there's a number of models out there to model the the uniaxial concrete behavior and tension and compression. Tension will discount a lot of that, but the compression models that account for confinement. These are some, John Wallace most recently has done a lot of work, so some of his papers you could find some of the updated information. But for example, the concrete models still go back to Mander's model. And in analysis and in programs, sometimes you find piecewise linear approximations to this, the uniaxial steel models. But then one of the challenges, we're modeling the stress strain, the fiber response nicely, but then what's the acceptance criteria? And in fact, ASC 41 has very little in terms of strain in the walls. There's a few values here that are kind of buried in general guidance in terms of concrete, in terms of strain and rebar or in concrete. And even the calculation of that strain is very sensitive to what gauge length you use in your analysis model. Remember, strain is delta over L. So what's the L and what's the delta? Typically, if we're thinking of plastic hinge in a wall, we want to think of that gauge length as being roughly the plastic hinge dimension, because that's the one against which we compare our acceptance criteria. Locally, there may be very higher strains than that, but in terms of what we could compare to based on tests, we have to have a common gauge length assumption. So this is from again, the ATC 72, some figures John Wallace put in there, just showing, you can't see the figures clearly, but the point of this is to say, if he did a model where he modeled each segment of the wall with a height equal to half the wall length, an estimate of what the hinge rotation could be, he got pretty good agreement between the calculated strains averaged over that length with measured strains based on tests. In finite element models, we sometimes hear, well, you refine your model and you're going to get a more exact answer. But in this case here, in fact, when you go to a more detailed model, you tend to get very localized measurements of strain, which are then become far apart from what they are in the test. So this is where the so-called art of analysis and engineering comes in. So, and I think Graham Powell, who's worked a lot on modeling walls, really will advocate, for the gauge length, if you will, or for the size of these elements, to pick them as a story height or half of the wall or pier dimension, not to go finer than that to avoid these sort of problems. This is some example of, again, some data that John Wallace shows, is that if you have a symmetric wall, that's shown in the plot in the upper right, our fiber models do a great job of modeling that. Basically, this is a wall with light axial loads where we're cycling it, and this is really just showing us that we could model yielding steel very well, because that's all that's happening. Cracks are opening, the steel is yielding, and vice versa as it cycles. The T-shaped wall shown down below, it's not quite the same thing. This is one where when the T is in tension, again, we have a big compression area. We're basically modeling steel yielding. So the upper right quadrant of that stress strain we do or load deformation we do pretty well. But when the T goes into compression, the strains get very high, and this shows our analysis models are not doing as well in those cases. Okay, so if you have a concrete wall with very high axial loads or a geometry that makes it prone to high compressive stresses, be careful. Another thing, we talked about the walls being shear controlled, that is, modeling the shear in the wall as elastic. So the shear checks, that's kind of a strength controlled check on the walls. So typically we'll take 1.5 VU, VU being the mean value, and comparing that to the expected strength of the wall. That's if you're in LA. If you're here in San Francisco, it's 0.75, because we put the phi factor in there of the expected strength. And Farzad said it's just 0.75, but when you're talking to an architect and this is driving the thickness of your wall, that 0.75 is a big number. To kind of start to get around that, some folks have said, well, that expected strength that we're getting out of the ACI equations, even if we use expected strength values, is really a lower bound to what the strength of the wall is. And this plot that's shown here is showing that the shear strength of a wall actually depends on how much rotation ductility is imposed on it. So if you have a wall that has very little rotation capacity, this is showing you can get shear strengths that are 1.5 times and larger times that given from the ACI formula, even using expected properties. But be careful, because as you get more rotation ductility, that shear strength will go down. Okay, and if you think of your actual wall, sometimes the place where the shear might be most down at the base of the wall is also where you're hinging it the most. So if you're starting to take advantage of some of these added shear strength based on tests, be aware of this coupling, that when we say it's strength controlled, we don't always couple the fact, well, the shear strength we have is affected by the rotation check it's kind of a separate check. What's the strain of the rebar? And then let's check the strength of the wall, but the two have some coupling. And there are data like these available to help us sort through that. There's continuing research to kind of develop better models that might actually, in these fiber wall models, actually combine the shear and axial effects. Coupling beams, a few different strategies. This is showing rotation springs or shear springs. Again, there's evidence. Some folks like to do it one way, some the other way. If you calibrate it carefully to tests, you can do it either way. Some warnings down there, and again, this is from the ATC 72 document, that that the effective stiffness of these coupling beams tends to be much less than what conventional 0.5 EI might suggest to you. In the interest of, I wanted to talk about steel brace frames here. The next couple of slides talk about brace buckling. I think, one, in the interest of time, and two, if you have a new tall building, I don't think you want a buckling brace in it, okay? So you can model those things, and we have neat models to do that, but let's skip that. So what you want is, if you have a braced tall building frame, and this is not to be selling buckling restrained braces, but a well-controlled yielding mechanism there, which fortunately we can model very well. It's basically steel uniaxial behavior. And a big advantage of using a nonlinear dynamic analysis in these BRB frames is that it gives us a much more realistic estimate of what the axial load developed in the columns is, because simple capacity design theory might say, or principles might say, design your columns such that every brace is yielding, which is unrealistic for a very tall building, but that we could get more realistic estimates from our nonlinear analysis. I only have one slide on response modification devices, but this might be one of the most important slides, because I think if you look at the future, how we make buildings better, it's going to be through some innovative devices that we put in. And the good news is that these are kind of well-controlled devices which we could then just build into our analysis models and take the guesswork about what a sloshing damper does to the response of a building, or a tune mass damper, or viscous braces that you put in. You just build these into your model and get the explicit behavior kind of out of the output. Unfortunately, the analysis models that are out there are starting to kind of incorporate, for isolators and so forth, like in the CSI products, you see those component elements to simulate those effects. A few slides on, there's many things about response history analysis we could talk about. One I just wanted to have a few slides on, is looking at viscous damping. Graham Powell calls this unmodeled energy dissipation. What that means is not that we're not modeling it in our analysis, it's that this is the energy dissipation that we're not otherwise capturing in our hysteretic elements. And then from a mathematics standpoint, it's what we're putting into the C matrix. And of course, there's different ways to, once you have that C matrix, you could formulate it with Rayleigh damping of proportional mass and stiffness, and kind of index that to percent critical damping at 2 values. You could use modal damping. Again, if you have damping elements that you're putting in your structure, viscous dampers, you don't want to put an effective viscous damping. You just model those velocity-dependent dampers directly in your analysis. But talking about the so-called unmodeled energy dissipation, what we toss into the C matrix, I'm going to skip this slide. But what's most important is to think about what is the energy dissipation in our structure that we're not modeling through our hysteretic components, our BRBs or yielding in the shear wall. There could be some things in the structure, cracking of the concrete slab that we might not think about that has some energy dissipation. A lot of non-structural components, again, kind of wall cladding and so forth. And then also substructure and foundation. If you use Farzad's model where he glues the building to the ground motions there, you're not taking advantage of all that radiation damping. So those are the things that we toss into this C matrix to take advantage of them. These are some measurements of buildings that Anil Chopra and Rakesh Goel put together. You could say, well, how do we know what value of damping? Let's go, after an earthquake, measure the decay in the response of a building, and that's our damping. Well, that would be wrong to put that in the C matrix, or to put all of it in there, because what you see about the damped out motion in a building, some of that might be things that you're actually modeling in your analysis through hysteretic response, and it's the part that you're not modeling that you want to throw into the C matrix. And it's shown there's a lot of evidence that as you get to taller buildings, if you think about the foundation effect and so forth, the amount of damping is going down. And it's also amplitude dependent. So if you look at responsive buildings under wind, you get much smaller damping than you do, say, under earthquake motions. So it's a complicated problem. You know, I'll just come back to the suggested values, and there's a nice 10 pages that I agonized over on in putting for ATC 72, so I'd encourage you to read all of that. I sent it out for review, and I got hammered by the reviewers, and I think it improved that. So, so anyway, you could read more of the details there, but the bottom line is we still say, you know, the damping should be pretty small, 1 to 3%. And sometimes it's even good to look at the sensitivity of your response to the assumed damping. And if it's very critical to that, to think carefully about that. Last couple slides, because I need to wrap up. I'm over time already. Just analysis software attributes. These are the things to think about if you're going out program shopping. You know, what are the nonlinear capabilities? How good is the analysis program at outputting data so you could process all these statistics? One of the groans from the engineers is when they have to ask them to run more ground motions, it's not just the computing time, it's that they got to take all that output and process it, get statistics and all these plots and so forth. Some programs have better features for that than others. I won't attempt to rate software, but just listed some here that are the ones that, and certainly for these car wall buildings, I think it's no secret that the CSI Perform 3D is kind of used on a lot of these. I also see LS Dyna, folks at Arup have used that, and the other CSI products and these other things here. Abacus and OpenSeas being for more kind of detailed modeling where you're trying to really dig into something. So last slide is quality assurance. You know, when you run a nonlinear analysis, hopefully it's not the first analysis of the building that you've done. Hopefully you've done a lot of elastic analyses and get comfort in how your building's responding, response history or modal analysis, even do some elastic response history, even some single degree of freedom to know sort of what deformations to expect. Well, we've gone past pushover analysis because that doesn't pick up higher mode effects. Sometimes it's good to start with a pushover analysis just to help validate that your model's working. You know, that some odd behavior is not happening, to kind of debug your analysis model. And then when you get into nonlinear dynamic analysis, to look carefully at hysteresis plots you're getting, do a little sensitivity study, see if it's well behaved. You know, the bottom line is really just have confidence, know what your analysis program is capable of, and that you and the people working for you understand all the features of that and kind of using it properly. So with that, thanks. And
okay, so before lunch, we're going to have a